ACMT telescope there in Hawaii. And Jessica got her PhD in Australia from the University of New South Wales. She was, I believe, the first woman that went to the South Pole to do observing from Australia as an astronomer. And she has done research in the cosmic microwave background experiments. And today she's going to tell you about harnessing the opportunities in the approaching radio astronomy renaissance, which sounds very exciting. So take it away, Jessica.
Thank you. Thank you very much. It's an honor to be here. This is actually, I'm embarrassed to admit, my first time adventuring here to you all at CFA. And thank you for putting on the gorgeous snow, which is still a novelty for me after nearly a decade and a half in Hawaii. So this is lovely. And yes, I'm gonna rollick you through a whole range of different things today, and I want to talk to you about basically how do you build discovery engines. And I've been very lucky with my background in instrument science and having fun building things at a range of different wavelengths. I've had some course to think about what is that magic blend of things that you need to do to really open up these new windows and these new frontiers in science. And this has come up a lot for me lately because I've really had to go back to school coming to Astron, because now I'm back in these low frequencies that I ran away screaming from when I was 20. Because at that point, it had been done. The hydrogen had been mapped, what else is there to do? And so coming back 20 years later, I really have fresh eyes on the frontiers we're starting to open up at these wavelengths and with these technologies. So I want to give you a little bit of an update if you are not familiar with Astron, who we are and what we do. And that's important because then I'm going to run you through LOFAR. This is our low frequency array that is based first with its heart in the Netherlands and across Europe. And I'm going to walk you through why I find this a case study in how to build a discovery engine. This is really important because we're now about to step up and we're about to scale up in this low frequency radio astronomy into the 2030s, and I want to talk to you about why I find that interesting. And then I will talk to you about the 4 questions that, at least because I am committed with Astron in the Netherlands on 2 of these major projects, both LOFAR and SKA, which is the 4 questions that keep me up at night in order to make this a success, and why this is sort of some interesting things to discuss. So we have a mission with Astron, which is the Netherlands Institute for Radio Astronomy, to make discoveries in radio astronomy happen. We do this by not only focusing first and foremost, we are a research science institute, we have a very large arm of active radio astronomers, but we also are a technical institute as well as an observatory. And so we have these 3 different prongs where we try and keep our expertise across the radio fields in order to not just make science impact in astronomy and engineering, but also with big, strong industry contacts and connectivity, and also because these things often have great knock-on societal benefits, especially in some of these radio technology developments. Astron is in the boonies in the Netherlands. I didn't realize they would have boonies. It's a whole 2 hours out of Amsterdam. It's a very long way, if you're asking a Dutch person. And it's in ngVLA, beautiful forest, out there near the German border. And actually this year we are celebrating our 75th anniversary. And the cool thing about this is essentially the history of radio astronomy. Radio astronomy in essence is less than 100 years old. And a lot of those original developments did actually happen with Oort and Co. here at Astron. We have about 200 people. We actually are a multi-pronged organization. We have Astron itself, and then we also host Jive, which runs the EVN, Interferometry Radio Astronomy Network for Europe. And we also have NOVA, which is the optical infrared instrument development arm for the Netherlands. So we have these 3 arms that I mentioned. We operate LOFAR and the Westerbork telescopes. We have our astronomy departments. And we have our innovations and systems, which is a fancier version of R&D, which works on all the technical developments front through to back end, and then into processing for all of our radio telescopes. And I think the Astron edge has been, over these 75 years, it has always managed to be on the cusp and on the frontier of the current radio technologies. And I'm very lucky in my office, I get to look out at the beautiful ngVLA telescope, which for 2 whole weeks in 1956 was the largest radio telescope in the world. Dodgerel Bank then came online, and that was done. But it's been a fabulous instrument. In fact, it was then taken over in the 90s after being derelict for a long time. They refurbished it, and it's now used by a volunteer group. They do actually a lot of really cool work with it still. But of course, then into the 60s, and you had the advent of the first interferometric arrays, which of course the Westerbork telescopes were a leading contributor to, and they still are operational there. We both contribute and work mostly now with part of the EVN network. Two of the telescopes there are in constant use. I'm going to talk to you a lot more about the next generation that happened after that, which is LOFAR. And then, of course, we are now the lead for the Netherlands in our partnership share in SKA, and that will be our next steps. So I had cause to think about this is how do you predict where you need to be in the upcoming landscape? What are the things the things you have to consider when you want to build a discovery engine and make sure you get it right? And I think to do that, you have to be a student of history as well as science. So you have to understand the drivers that create new discovery space and balance instrument push, or you would be saying what the engineers want to build and what the scientists want. Finding that happy space in between those two allows you to measure a value of a scientific instrument. These things, when you combine them, can inform a future science strategy. I was at Paul Ho's retirement conference in Taiwan, and we talked soup dumplings a lot. So this was what got me in the idea of the three things I think you need for a discovery engine. First one is a wavelength window. Anytime you open up a new wavelength access, you equal new science. The second one, dimensionality. So you could be going into a different dimension, time domain. You could be going into multi-frequency. You could be going into polarization. But every time you bring a new dimension in your instrument, you are also going to be opening up a discovery space you didn't have before. And the third one is almost the most important. And I just call it scientific greed. More, whatever it is, whether it's resolution, sensitivity, field of view, multi-object, bigger, better, faster, stronger. When you have an instrument that combines all of these three things, you are guaranteed to be opening up new science discovery space as a result. And the example I'm going to bring to you now is LOFAR. So LOFAR, when it was originally conceived, was actually going to be testing a small-scale test to start to drive down to that epoch of reionization sensitivity footprint. This is a search which 15 years later is still going on. We're still driving down onto those noise limits. But that was just what it was meant to be, a single experiment. And it was also meant to be a pre-SKA. At that point, SKA was going to be operational by, I think, 2020, which is adorable. But this is still an experiment for EOR today, but it is a lot more than that. So here, I've got a bit of a lag, there we go, is an example of the two aspects, a high band and low band antennas. They're about as simple as a telescope can get and almost as boring to look at. I mean, it really is a stick in the mud, particularly in the Netherlands, but we have 38 of these stations around the Netherlands and then several more through Europe. And it is an entirely digital telescope. Nothing, no moving parts. Everything is moved and steered by signal delay and combining by different beams on the sky. We have these two sets, and you can see there the frequency ranges that they span. And currently we can do one or the other. We cannot do them coincidentally. Everything now is bottlenecked in terms of the data regime we have to deal with. We have these high bandwidth fibers that send back to a Groningen central processing facility, and then we start to image. And this is a slow, slow process. This is what the array looks like. At the moment, the two new ones, which we're very excited about and don't exist yet, because that's why they have the dotted lines, you'll see Italy and Bulgaria are stations which are going to be very interesting for us. Because as you know, the further apart we get these, the higher the possible resolution we get on the sky. In fact, when we did some maps of where the best next place to put one would be, weirdly, we're calling it the Belgian Hole, which is a great name for a bar or a pub, I mean, or a band, or maybe a pub band. So that's actually one of the spots. We do need that to fill in the space. But these two will make it the highest resolution, low frequency telescope on the planet. So I mentioned, right, we started in this EOR. What is the example here that tells you that you have a discovery engine on your hands? It is when you start to look at the breadth and depth of the science that is now being utilized and found with the LOFAR facility. And some of these might be, understandable suspects in fast radio bursts, in galaxy clusters, pulsars, SMBs, but we're now getting into the space where we're doing far more interesting things, and some of these things are truly surprising. I don't have time to go through everything, but you might be familiar with this little guy here. To give you an idea where the LOFAR mapping comes in to give you the scales of this is you can really scan out these sort of 500 megahertz regimes. You're starting to map those large-scale structures on the sky that really are embedded in some of these supermassive black hole events. So we go and chase after those huge streamers, and this is really some of the bread and butter work that LOFAR does. Wide field surveys have been, of course, where we find all of these guys. We have 3 major surveys at the moment. These predominantly use just the Dutch stations. The obligatory plot where you see the sensitivity compared to some of these other sources, and you'll see the lots and the lots deep field, which is the DD ones there. Here are just some examples of some of the beautiful images which some of these surveys have come out with. 6 arc-second resolution is what we can get with just the Dutch stations. Okay, so you're dealing just with the Netherlands. It's quite small, so you only have a couple of 100 kilometers across that. What gets interesting, though, is when you start to do these same pieces of sky, but now utilizing all of those arrays that I showed you across Europe. Now we're getting down to 0.1 arc-seconds resolution, so about Hubble mapping speed, but at these incredible low frequencies. It is incredibly time dependent. There is one particular postdoc who needs to look and eyeball this, and you then put one of these fields through for about 3 months of processing. And right now, that's the bottleneck that we're trying to overcome. But you start to shift from this kind of resolution down to things where you start to actually be exploring totally different regimes in terms of some of these structures. And if we can get this processing bottleneck through, this is something that we're intending to do across the entire LOTS fields. Of course, you would never have predicted, in my mind anyway, that we'd be doing exoplanets at these radio frequencies. But this is actually the aim with our next upgrade to LOFAR. Right now, we've successfully seen circular polarization of the magnetic fields around brown dwarfs. And we do believe that with the increase in that sensitivity, this is going to be something which we can also map because of the magnetic fields around Earth-like planets. And talk about unexpected discovery space. Normally you have to pack it in when you're having a big thunderstorm overhead. But now we're actually using these events, and we can map lightning in real time overhead of the LOFAR stations. And so we're actually venturing into meteorology. I did not realize that the lightning structures and how they evolve is not actually well understood. These are actually some of the first real-time maps of lightning events that have ever been done. So this is just a random and extra cool part of the scientific frontier that we are opening up at these frequencies. I'm a metrics nut, and so how do you measure scientific value? One of the things I always measure is who's using your telescope. How many people are collaborating on this? Over the 15 years that we've been observing, we've had a 3 times increase in publication numbers, but more importantly, I find you see the increase in collaborations. We have 30 countries, 400 unique PIs, and over 2,000 co-authors, just in the subset from the last 5 years. And then I'm going to put some controversial plots up here. Don't throw things at me. We can talk about them afterwards. If you go up and you start to look at the median impact per paper, right, these are the ones which really take notice. I actually have only put these 4 up here because I'm talking roughly radio wavelength interferometers on here. You don't get on Dennis's plots, though, unless you're in the top 10% already around the planet. But what's interesting here is LOFAR wasn't even included in these statistics when I asked him to do these. I was even stunned at just how high impact some of the papers are that are coming out of the LOFAR telescope. If you want to be even more controversial, well, actually this one's cool, because one of the things here is I just loved how high the SMA comes in on your altmetric scores. So here you're looking at things which are not the typical impact that is measured straight out of citations, but social media, news articles, books. And this is a very interesting one to see how much traction is your science getting in the non-traditional circles. And so I like the fact actually that SMA and LOFAR are right up there together at the top of this plot. If you game, you can also then look at things like, well, we always quote total impact. If you're putting out a lot of papers, of course, your impact is going to be huge. And that's why you have ALMA right up there at the top of the pops. We're combining here the impact of each paper by the number of papers, so that's going to really blow you out of the water. But if you then say, but if you know how much these operations cost, then you can do something like this. And I couldn't put Sophia on here and make the scale sensible. But what's really interesting here is now you start to get into, are you getting value for money? And here is really an interesting argument because this is just cost per paper. Really blatantly. Dennis refused to do this. This is just something that I put together. Or how much value per impact. And this is where I sort of say that total impact per cost. And this is interesting to me, just dividing the impact by the cost per paper. And your median impact for cost, and suddenly LOFAR is one of the third most value for money telescopes that we currently have in operation. So this is just yet another aspect where you can start to look at and measure value, and it is all different ways that you can do that to start to understand how much you should be pouring into your infrastructures. So how do you make sure if you've got an instrument that you then keep it competitive? And in my experience, keeping expertise in-house is vital. You need to continually know the state of play, who is out there, what are they doing, and don't be afraid of competition as well as complementarity. There have been a few facilities which have said, oh, we won't do that because X is coming along, and that ends up being another 10 years down the track. And I would put LOFAR and SKA as examples of that. So I was going to check our new LOFAR 2 upgrade, which we are just getting kick-started now, off with my parameter space for is these worthwhile things to do in terms of my greed and my dimensionality and my wavelength range. So this is LOFAR 2. We have funded this. We are setting up now. We've just got all the hardware in place, and we are just about to scale this up. I mentioned we could only do high or low frequency before now. Now we're going to be able to do both at the same time. We are doubling the number of receiver channels, and we're improving our calibration. So this is going to speed up a lot of things that we need to do. It also is going to broaden the amount of wavelength that we can do it over. And so this roughly is going to give us the upgrades we see there. It's going to give us a really big boost in sensitivity, and it's going to give us a really big value in return across those additional wavelength ranges. To give you an idea, compared to SKA low, when we do the upgrade, which is Duplo, we'll have 5 times more frequency in the lower end than SKA low, and have more than 10 times the resolution. This is actually our first light of our test array. And you can see the old chestnuts of radio sources in the sky. I actually liked this little snapshot because you also see us picking up a thunderstorm on the horizon. So you get to actually see the sensitivity there to the lightning, which I thought was actually pretty cool. So we're really underway with this. We're expecting to be fully integrated, tested, commissioned, and underway for 2026 startup. We are already thinking about our next upgrade. So now that we have managed to do all the frequencies all at once, the next bottleneck we have is in getting that data back to our correlator. Right now, we're limited to a 10 gigabit per second line. Just upgrading to 100 gigabits per second, and we're going to go up a factor of 10 in sensitivity. So just simple things like that now are the bottlenecks of pushing that back to the processing steps. At the moment, we're capitalizing on about 1% of the potential data that we could be collecting from the sky with LOFAR. We just can't handle more data than that. The focus I'll put here, though, is while we're doing that upgrade, most of the next generation is going to be going into our processing commitments. And I'll give you an example of why we need to do that in a minute. All right, so come with me now into where we're going to be at these low frequencies in radio astronomy in 2028, because the field is getting pretty crowded. If you start down with LOFAR 2, we've got that low frequency end covered, and then you're going to have SKA, which I'll talk a little bit about in a minute, coming up through to the 350 megahertz range with SKA mid in South Africa. And I'm not even adding here all of the aspects that are on here. So of course we're talking about ngVLA, we have DSA 2000, and we have a host of other smaller ones, including Argos, which is getting underway in Greece, that are going to fill this landscape in a range of ways. But it is significant that you are actually talking about investment scales in radio astronomy, factors of 100 greater than they ever have been before. So there's a reason for that. So the SKA is the first one that I'm going to talk about. And you will have probably heard about this, of course. We call it one observatory, 3 sites, the UK headquarters, and then we have the SKA low in Australia and SKA mid in South Africa. And you can see the frequencies. I'm not going to go through all of this. The key thing here is we are finally in construction. We started construction in December at both sites. This is excellent. They are currently scaling up their employment. I think they're at about 200 of their aimed for 500 staff across these 3 sites. About 75% of the funding for what is going to be a 1.6 billion euro or dollar project, with an expected lifetime of about 50 years. And essentially, whenever it says, who's the members? I'm like, everyone but the US. And it's almost true. We actually can say now India has now just signed on for this. We're expecting all of the rest of these to join us very soon, and you can see the initial member states here. And the reason being, no one here on this list has a share in SKA of more than 18%. We're getting to scales of funding where people just cannot afford to go all in on the size and the cost of these facilities. So this is why I am calling the 2030s the radio astronomy renaissance. We've before now had a high barrier of access. Right? If I hear black belt radio astronomer one more time, I'm going to scream. But it is about these interferometric, the calibration techniques, the processing requirements. You can't just click and say, hey, I want to observe that and get some data and go away and do it. Not at the moment and not at these frequencies. Everyone has their special one-of-a-kind method that you have to go and ask someone to do to get your data out. We can't do that with these generation of billion euro and dollar instruments. And ALMA is an example of opening up a wavelength space to a new user community that hadn't previously done that before. And I do expect to see this now in radio astronomy at these low frequencies as well. And that's why you're seeing funding going into these frequencies at the scale you're seeing it at now. So here's the 4 questions that are sort of keeping me up at night with all of this, because otherwise it looks fantastic, right? Look at all of these incredible things which we have on the horizon. My first question is bigger better? I was lucky enough to be at the SKA mid-site, and they had, of course, incredible Meerkat telescopes there on one side, and you can imagine now, what all the SKA mid-dishes added to that's going to look like. I turned around, and there was the HERA experiment there. And it was chicken wire, some PVC pipes, and some cable ties. And I was like, this is an EOR experiment that, could eventually have Nobel Prize on it. Like, you can still do incredible radio astronomy with chicken wire and PVC pipes. So I always question, do you need to scale everything up? Or can you be clever? Can you find a niche no one has opened up before? And we're dealing with the scale factors are really going to hurt us now, because there's things we haven't thought about. Where's our workforce? So I mentioned SKA needs 500 people, science, engineering staff in the next 3 years. They're already hitting bottlenecks. We're already stealing from each other, yeah? And we have these regional data centers which have to be at the same scale as SKA itself. And I was chatting to a few people at AAS, including NRAO and others, and it's like, we can't get people. Either it's our locations and or the fact that there's plenty now to choose from. So we're already running out of workforce. So I did some scale-ups of some of these models. By 2030, we're going to need a factor of 3.5 more astronomers, engineers, software developers, programmers than we have now. Where are we getting them from? We are not, at our current attrition rates, with our current workforce development rates, we would need more than 2 decades to get this workforce together. And then I don't consider a year good unless I've gotten into at least one fight with Elon Musk. We did actually put a paper out last year to show that, in addition, of course, to being the new problem for places like Vera Rubin and optical astronomy, when they put bad Starlink satellite necklaces up there, they also leak into the radio. So we've just spent all of this time going to the most remote places on the planet to get away from radio leakage, and it's up there anyway. To give you an idea, we have to employ one person full-time just to run around the Netherlands playing whack-a-mole with all of our digital telecom carriers, with all of the places putting in new solar arrays. We can see the windmills. And so we manage it, but barely. And this is the big one. Can we even afford to turn these telescopes on? With our new upgrades on LOFAR, we'll be creating about 70 petabytes a year of final data products, about 3 times that in intermediate products. SKA, just getting rid of all our intermediate data and just our final data products, is going to be about 1 exabyte a year. I did a calculation to say for every member share that they buy in 1% more, they will have to put an extra 1 million per year just on their data processing costs. Essentially, every dollar or euro of ops, you need another one for your processing and storage. That's also to point out, look at our energy requirements. Look at our carbon footprints. In Europe, for example, we're already being threatened with potential carbon caps on some of this. So if we don't get ahead of this, someone else is going to potentially do it for us. All right, so now I'm going to give you the good news. This is how we're solving these things. The first one is bigger, better. I will never tell you that you will build something from scratch is better than leveraging what you already have in hand. Anyone who's tried to build an instrument or a telescope knows how hard it is. You forget that and try to build something new and shiny because that's what politicians like, snipping on a new ribbon. But putting 1% additional into an existing tested infrastructure is always the best value. And if you can do that, do it. So what we're doing about next is, well, what can we do with LOFAR? One of the fascinating potentials is SKA low doesn't go below 50 megahertz. We're already down and doing fascinating imaging at 10. What if we went down to 5? This is completely unexplored space, and the reason being the ionosphere gets in the way. Yeah? So calibrating down at these frequencies are completely unknown. NENUFAR, which is in France at Dempsey, is currently testing down to these frequencies. We could actually very trivially upgrade our low-band antennas for nearly no cost and come down and focus on this, just testing it out to see if it's viable. Again, remember those discovery engines, opening up a wavelength that is untested until now. We don't even know what we're going to find down at these frequencies, but a guarantee that it might be worth finding out. The other thing we're considering is going in the other direction. We have this incredible footprint in Europe. We have all of the technical facility there on all of this infrastructure. What would happen if we go to a large N, small d system, kind of like Argos, we put a bunch of 1 meter dishes at all of the LOFAR sites? Turns out, if you put about 100 of those at each of the sites, you'd actually get a better resolution than the SKA mid and DSA 2000 with comparable sensitivities and integration times for about 1/10 of the cost. So there are some places to explore, and these are the 2 directions which we can't really do both. We're looking now at which of these 2 directions might we go in when we have all of these huge, big, large-scale facilities on the horizon, and where is that niche that we can best fit. What do we do to get this workforce up? Well, this is where you'd better hope you know how to stop the leaks in our current very leaky pipeline, and how do you create retention and inclusion as soon as possible. Because all of these wasteful funnels that we have right now, we can't afford to waste anymore. So retention, inclusion, minimizing attrition rates, and broadening our mind to the kind of people we want in the door, these are the ways we are going to accelerate that workforce development. Some of the things we're doing, I've got an inclusion strategist, which we're just in the middle of hiring. We're setting very ambitious targets for bringing in our underrepresented groups. Astron is, as I said, in a very remote location. We have to do everything to try and get people in the door. We've actually just started our equitable hiring campaign. These were actually two of the major papers in the Netherlands over the weekend. You can see we actually had host Jocelyn Bell-Burnell in December. That's me there saying, "Looking for women" is actually the title in Dutch. Don't know if that's exactly how I wanted it translated, but it's good because we're getting the note out there. And I'm really literally coming out and saying, "Where are you? I need you here." We're also partnering with tech training companies. These are companies that are taking particularly women who have been highly educated in other non-technical fields and training them in software. It's a really interesting apprenticeship program that we're working on. We also have a Bell-Burnell Fellowship. I'd like to say for any potential postdocs that it's still open. We actually just closed, but this will be yearly, 2 people per year. And the difference here, we're very glad that Jocelyn was happy to lend her name to this, being as we think of her, basically creating an entire field in radio astronomy. But our focus is not just on research. This will be someone, we want to catch those people who don't just want to do 100% research, who might want to stretch into instrument development, into projects in software. And so we want to keep the prestige of these positions for people who are a little bit more out of the box. And that's what we're hoping for. Okay, what happens about being deafened? A few things. We are mitigating, and some of these mitigation techniques are actually working quite well for now. The other interesting thing is right now Starlink is willing to talk with our engineers and our astronomers. So they want to know what they're doing wrong and maybe send up better shielded Starlink satellites in the future. We, of course, at least will say, well, that's at least better than nothing. But, of course, Starlink is only one of the constellations which is going up there, and they're not even the largest set. And so we thought LOFAR would be impossible 10 years in because we thought of the ever-going increase in the radio background. And we're here 15 years later looking at another 15. So I don't believe that it is entirely a lost cause, but we are also looking at other exciting developments. These include CubeSat satellite interferometry clusters. So this is something which we're going to be partnering with Astron in the Netherlands and others to start to test. And we're also talking about, and I can't believe I'm saying this, but we're also talking about inflatable low-frequency arrays on the moon. And so ESA is actually looking for a next mission payload on this. So we just had 3 or 4 conversations about this. Having a low-frequency EOR test-like experiment on the moon might be another step in getting ahead of some of these challenges. Okay, and the big one. Can we afford the data footprint? And it's like I usually say go hard or go home, but I say go hard and go green. These are the 2 aspects we need to absolutely succeed at if we're going to afford this. So currently, with the current data costs, and with our currently available usage on processing and on storage, we could turn LOFAR 2 on for 3 days. And then we'd be full up. That's it. And so when you do some calculations on the scales of the need, everything you hit is to do with your processing speeds. So right now, because it takes a lot of time to figure out how to actually reduce the data, that data sits there in that intermediate state for a long time. We can't afford to do this anymore. We have to push to low latency or real-time processing and then throw the rest on the floor. Essentially, unless we can do that, we can professionalize all of these algorithms to such a point where we can just get it done, reduce it, and have that footprint to deal with. We shouldn't be actually doing the science in the first place until we can afford it. And so for every $1 million you spend now on that pipeline professionalization, on the high-performance compute parallelization, you save tens of millions a decade from now in the amount of storage and compute that you've developed. So you have to put the resources, and that's what we're trying to focus on now, right now, on getting that professionalization done. We can't wait 10 years because we can't afford to get there. The other point is the environmental cost. Actually, one of the things which all of our young astronomers are saying, we don't want to do science in the future unless we're doing it in a sustainable way. We have a sustainability engineer coming. We've actually already mapped our entire carbon footprint of our facilities from end to end. And this was a really interesting experiment to go through and see where those footprints were. We're going to have our sustainability engineer talk us through targets that we should be setting and how we're going to get there. So prioritizing these efficiencies, these technologies, the algorithmic development will just both reduce our carbon footprint. Because what happens normally, right, when you do a processing gain? You use it to do more science, yeah? Whereas instead we're saying, okay, we're going to commit to a target of reducing and capping our energy footprint. We have to already improve to get there, and then any additional improvement will go towards more science. But we have to do both. This is an idea I'm actually talking about in extremity with the Economics and Finance Ministry in the Netherlands. This BOS is forest, so this is BOS compute. This is a concept for having a green computing technology development center based in the north of the Netherlands, which is an area which doesn't have a lot of industry, which has been very underdeveloped, and they want to see more come here. BOS compute is an idea that, kind of like mapping DNA, you map in very different science and medical cases the entire collection through to dissemination data chain, and every single part you turn green. Every single step in that chain, you look to either technologies, whether they're physical technologies, and we're looking at things like bioplastics in developing of batteries, bioplastics for circuit boards, which would eventually break down, things as simple as that, all the way through to making sure your algorithms and your compute is 100% green. You would then bring in groups and not have expertise in-house to come and solve those problems end to end. And you solve the fastest ones first. We're looking at about 350 million euros to try and fund this facility. This would not be something Astron would be anything but next to, because next to this center would be our Astron Green Compute Data Center. Just kind of like you have medical research next to a hospital so that you can test that out where you have these real-time solutions, we would be saying we will take all of these new solutions and we will adapt them in real time to the data challenges which we have in-house. So, we've sort of evolved our mission. This is something we've been doing over the last couple of years to see how we adapt both to this changing radio landscape, but also to the things that matter for our current and for our future workforce. And so we've added these things, which is we want to make radio discoveries happen for the greatest number of people, lowering those barriers of access to radio astronomy for more people, making that workforce development less leaky, more inclusive. And that discard rate needs to go away. And we want to return more into our society. So also having community which represents us, safe environments, but also making sure our science is sustainable, it's environmentally conscious. So I wanted to leave some time to chat. I do think that we're about to go into this new frontier space if we can afford the data, if we can get the resources, and if we can keep it quiet and environmentally clean. And I think then we do get to a place where we're creating this new generation of discovery engines. Thank you.
Okay, thanks, Jess. Questions? Okay, V then Kurt.
Carrie can go first. Oh, sorry. Oh, okay. Sorry, I wasn't sure if this was mine. So, thinking about how to build into the workforce, I think a lot of us, I think it's changing slowly, but the idea that you're providing not alternative, but just a much more, a wider range of career paths is really important. I think that fellowship is actually a really great idea. It's something, expanding it to what we maybe traditionally thought of as purely research track is I think, the 21st century thinking. Having said that, it's still a very narrow pipeline that goes into that training. So are you thinking about bringing people, because if you're talking just people primarily who are PhD trained, they sort of envision a certain track, and that can be a bit difficult to peel off from that. But are you thinking about building it even earlier, like basically even before university?
I want apprenticeships in astronomy, right? I want people to be able to walk in because they can't either afford to go to university and are starting straight out of high school to come and learn how to build a telescope. And you provide them apprenticeships to step into other levels of whether it's engineering, computer software, all of these things. And if they want to eventually go and get a PhD, awesome, we enable that. But I want to bring it all the way back. And I want to take those barriers of assumption that PhD astronomers, there's work that we're doing here, especially in the high performance compute, PhD astronomers have no business doing. There's the amount of times that I spend at Astron taking these jobs out of astronomers' hands and go, you've got better things to do than this. You should be working on the science, not working on the compression algorithm for this particular bit of software. And so there are things now, because we're scaling to this rate, that we shouldn't have astronomers doing. So that definitely is a change up that we need to make. And so no, I'm not married to this concept that just PhD astronomers are going to be in charge of these workforce developments. In fact, they can't be, because we want our PhD astronomers out there on the science frontiers playing with the data, not in the back box, unless they want to be. So instrument science, which I'm biased because that's where I come from, is a notoriously under-recognized area, because you build an instrument, you don't get a lot of publications out of those, right? And so reward and recognition due to our academia and encouraging people that there are other ways to get this kind of recognition and satisfaction in a career, we need to start that as early as possible. Because I adore my pure scientists. I love you all, but I also want the people who don't want to do that. Right? I want the ones who like getting their hands dirty and might be more interested in tromping out with me in the mud to fix some antennas or working on some of these software or the AI developments that we're doing in these sorts of things. So it is really about that diversity of interest as much as anything. Catching them is hard. That's something that if you've got ideas, I'll happily hear your suggestions.
We had Carrie. Did you want to ask your question?
Yeah, so did you want to?
No, you
Okay.
go.
So there's a few things you mentioned, that kind of need cultural shifts. And one thing that I've noticed, there's a few things that you could have taken out of your presentation and put pretty much in any astronomy presentation, and they would say the same thing. The data is the big problem, the processing, collection, and all, and that's all a big problem. The software needs to start being professionalized, right? Those two things are happening. I spent a lot of time worrying about that and how to do that. I have not seen the entire industry, though, when I say astronomy industry, making that cultural shift. And to me, everybody seems to have identified it. I've seen a lot of that. But as a whole, it doesn't seem to have been accepted yet. And what do you think is necessary in order to get to that point?
Well, for example, I got to the point with our LOFAR users community in Europe where I said, look guys, we can't turn LOFAR 2 on until we delete some data. And the screaming can be heard from here. Because they've been sitting on the old commissioning data from 20 years ago is taking up space, petabytes of space, and no one's looked at it for years. Oh, but we could go back one day and do that, you've heard this line before. So the idea of deleting data is horrifying to every single astronomer. That's something we're going to have to do. Literally, I'm doing that when we go back. There's been 6 months when we're deleting the first of the data because in the SKA land, LOFAR 2 land, you're never going to see those intermediate products. You'll just see those final data products. So just waking people up to that we can't do things the way we used to, that's the first culture shock, which is happening right now. Because SKA is kind of imaginary. I think the second one's going to be Vera Rubin coming online. I think the data deluge coming out of Rubin is going to be the second freak out, the shock wave that the community is going to need to see to go, oh wow, because you can hear numbers and you can see the petabytes or the volumes on screen, but I think until that's real, then I think people aren't going to come on board. But I think the terror of those two things will start to shift people to solution-driven. Oh, okay, we really need to actually make some hard choices here. But you're right, we're not there yet.
So you're talking about terabytes then, rather than terabytes.
Sorry?
Let's play on words.
Terabytes. I think in Dutch now, and my sarcasm disappeared along with that.
Peppy had a question.
Okay, let's talk. First, I have a comment and a question. And the comment is that the shift in thinking to have professionalizing different areas of what we do is happening in sensitive fields. I work in Chandra X-ray at the end of the spectrum, and we definitely have a group of professional software people, and we have instrument scientists. And speaking of the software people, they are not PhD scientists. They just come. They're good at what they do, and maybe they did some computing in college or whatever, and come from industry, and works really great. And so I applaud that you guys are thinking the same direction. I think is the way to go. The question I have is looking at the big picture, the fact that we have all these data, different frequencies, and we all want to use it in a way or another. It's important to be able to speak to each other. I mean, it's important that the data be able to speak to each other. And so we need some kind of standards. And here we've been working with the ngVLA. I don't know if you heard of it. I wonder what your ideas are in this sense.
Well, talking of cultural changes, I mean, radio astronomers don't play well with others, is one way to put it, and getting them on board with the idea that someone else might be interested in their data is still a shock. So we're a long way from that. But I'm seeing these wheels reinvented on a range of different things, and radio astronomy at these frequencies is the last of the party, so we just have to adapt. And there's a whole host of opportunities out there to do that. So we just have to, go with the. Where is that community, going to be? How do you make it as accessible as possible to the most people? Pick that standard and run with it, and not get too precious about. But ours is better. Just make something which is actually functional and adaptable across those ones. And that's why we need to investigate and try not to start everything from scratch again.
Okay. Any other questions? Okay. Shep.
Thanks. I have a two-part question. This is a great talk. One thing I haven't heard mentioned on the workforce area yet is competition with industry. And what kills us is that we put an advertisement out for a software person or algorithm person, and they can make 3 to 5 times what they're making here at Google or Amazon or name your company here. There are some ways we might get around that, so we could have internships where they come from industry to academia to work for a while and then go back, so that people who work in industry can have the fun of black hole or star forming research, and then go back to looking at slide bars, up and down on websites. And you could think about something like that. Have you thought about how to handle that competition?
Yeah, I mean, to give you an example, SKA, what they've had to do is they've had to create a special category of jobs, because they've acknowledged that their pay scales just don't compete. So for these special, you can't get them anywhere else, software development jobs, they are just putting their salaries up at the same level, because otherwise they're not getting people in-house that they need. So that's one of the aspects. I'm a bit more controversial. I'm like, why aren't we just working with Google? Why are we building our data centers why are we having to do this from scratch? They're doing it bigger, better, faster, stronger. Why aren't we just using the space? This has already been solved a dozen times over. They would laugh, Google, at the petabyte issues that we're talking about here. It's a controversial one. We're used to being independent, doing this stuff ourselves. I'm asking why we need to. So one of the things we're doing is creating what we're calling these accelerator hubs at Astron and Astron, which are essentially going to be plugs into data center development places. We're not going to try and be all things to all people. We are going to have a high-performance compute core surrounded by a layer of scientists who are the interface with our scientists and doing the algorithmic development. We outsource all of the real development to the data center experts. Don't even try to do this from scratch anymore. So that's the other way that I'm looking to go. I don't think we should be trying to do this all. I don't think we can.
We had another question at the back there.
Yeah, so thanks for the talk. So this is a very LOFAR specific question. I don't know much about LOFAR, but what I understand, you can, while seeing the whole sky all the time, you can only look at one phase up to one specific direction.
Yes.
And I guess because of data rate or the limitation, it seems like in the LOFAR 2.0 it's getting even worse.
Yes.
So how do you deal with transient science, where you probably, in principle, could look at the whole
Yes.
sky and see time variability at a short frequency, and or in turn, if there's some triggering event, is there a way to look at this simultaneously by other observations or
Not the last one. The first one is, yes, we have multiple different modes which we can observe in. We have a transient mode. Of course, we have a fast radio burst mode, very similar to chime, right? You're going up there, you're grabbing what you need, you're throwing the rest on the floor before you take it to processing. So it's really our imaging, which you're describing in the first one, where we're limited in what we can do on the sky, and that is all bottlenecks on the data. I think we did a calculation we're looking to do next, is if we had a full field of sky, actually every second at the highest time resolution for like 24 hours to just see what was up there. I think it was going to be an exabyte in 24 hours. So that sort of gives you an idea of how much you have to throttle back on the capacity in order to just do what you do. But there is adaptable modes for all of the things that you described. The one which is the most data intensive right now is limited to high or low is the imaging.
I'm a first-year PhD student, and I'll be entering the workforce right around.
Sorry for this really exciting talk.
Thank you for the talk. What are the things that students who are current students should be doing to prepare for this upcoming renaissance?
I mean, do you have a big enough bucket to catch all of the science potential in? I mean, you really are just going to have to be, choose your own adventure. And someone came up in at the AAS, but I don't like multi-messenger. It's just a bit wishy-washy. Someone said, I'm panchromatic. I quite like that, but be panchromatic. I mean, the thing is that the frontier space isn't just in low frequency. And the more adaptable and flexible you can be across wavelength space, the more interesting the opportunities are going to be for you, because then you do get to choose your own adventure. I'm aging myself with that. People who are younger than me won't know what a Choose Your Own Adventure book is, but I'll explain it to you later.
Any other questions? Okay, if not, let's thank Jess again.
This is Christine Dempsey. I'm a big LOFAR fan. We do X-ray astronomy, but we become big LOFAR fans.
Reinhardt's one of our best friends.
Oh,
Yes.
fantastic. All right, well, that makes a lot of sense.
So he came here just after his PhD.
Yes.
And we stayed friends. And various other people, mostly now through Bologna, have now come here. So there's a small core.
We have a big Italian here.